Okay, so before we get started talking about sensation and perception, I want to ask you a question, and for this particular question, I don't actually want you to answer it. It's kind of rhetorical. I want you to just reflect in your own mind and think about it a little bit. And the question is, have you ever hallucinated? If any of you want to share, I don't know how appropriate those stories would be for this class. I'm going to guess, though, most of you probably have not hallucinated unless you have been under the influence of some sort of substance that might make you. Yes, Royce,
Yep.
right? Yeah.
I actually, when I got my wisdom teeth out, the pain meds, whatever they gave me,
Yeah.
made me like see stuff in my sleep.
Okay, interesting.
I was like my dreams. I'd wake up, they'd be happening in my room.
Okay. So your dreams carried over into your waking. Amy, right? Okay.
I did when I had a fever of like 105, and I also had a migraine, and it just really screwed up my vision. I was just so much good at weird things.
Okay, all right, interesting. So a couple of you have hallucinated. Yeah, Scott.
The military loves sleep deprivation. Definitely makes things not where they're supposed to be.
All right, interesting. Yeah, sleep deprivation will do that for sure. Okay, Devin, right? Okay. I would say that probably technically counts as a hallucination, yeah. Yes. Okay, so a few of you have. Sounds like all of them have been under some sort of abnormal circumstances. Again, probably other stories that are not as appropriate, which we won't get into. All right, so, whenever I'm talking about hallucinations, what kind of things do you think of? Like, what are some other circumstances where someone might have hallucinations? I heard drugs. What else? Yeah, Miranda. Yeah, so someone who's suffering from some sort of very severe, psychosis or mental disorder like schizophrenia. Okay, so we tend to think of hallucinations as these things that, are not normal by any circumstances, right? A lot of us have probably never experienced hallucination at all. If we have, it's because we've been under some sort of drug or sleep deprivation or something. Okay, let's get into this a little more. Can anyone give me a good definition of a hallucination? Like, what even is a hallucination? Yes, Amy. Okay, so seeing something that isn't there. Okay, so Royce mentioned something about dreams, right? You said that your dream was carrying over. How many of you have ever had a dream? Okay, was that dream real? Were you seeing something that was really happening? No. So by that definition, we all have hallucinated, right? Can we come up with a definition of hallucination that does not include dreams? Yeah, Miranda. Okay, yeah, so usually once we wake up from the dream, then we realize, it wasn't real, we stop believing it. Yeah, Alex.
Receiving a physical thing that is not there while you're in a fully conscious and aware state.
Okay, so if we just add the caveat that you have to be conscious, so then that excludes dreaming. So hallucination is when you see something that isn't real and you're conscious. Okay. Processing illusion or inverted flag illusion. There's other names for it if you want to find it on your own. The projector doesn't want to turn back on now. Just give me just a minute here. Come on, you can do it. Why are you blinking? Uh-oh. That doesn't sound good. Did I kill the lamp? Maybe? There we go. Yay. Okay. All right. So, that's just one very basic illusion. We could get into the details of how that illusion works and why. We might talk about it a little bit when we get into color perception in a minute. But one thing I want you to know just from that illusion and from others we'll work with next Thursday, not this coming Thursday, but the week after, is this idea that we're kind of constantly hallucinating if you really stop and think about it in the way that our brain works and the way our mind works. Kind of like I was saying earlier, there's real stuff that exists in reality for sure. This table is definitely here, but my perception of it is very much constructed by my brain. by my brain just, taking all kinds of memories and associations of tables I've experienced in the past and combining that information with all this ambiguous like light that's bouncing into my eyes or whatever, and trying to make sense of all of that, and then basically puts all those pieces together to kind of tell myself a story about what I'm experiencing in my day-to-day, moment-to-moment life. So we're kind of more disconnected from reality than it might feel like at times. And I hope that's not unsettling, but that's just kind of the way that our brains and minds work, basically. So perception is essentially this process of taking energy in the environment. There's like photons of light, there's sound waves, there's all these different kinds of energy, and trying to then translate that into something that the brain can make sense of. We're going to focus mostly by talking about light and sound and vision and hearing, because those are the two senses that we know the most about. And when I say we, I mean me personally, but I also mean like the field collectively of, cognitive psychologists and neuroscientists. These are the two most studied senses. We have a lot of other senses that are not as well understood. How many senses do we have, actually? That's another thing we can talk about. So I see a couple of you put up their hands, 5. So I already said vision and hearing. What are the other 3? Taste, smell, touch. Those are the 5, right? Just like a lot of things we learn in elementary school, that is a massive oversimplification and isn't true. We actually have way more senses than 5. So right now, close your eyes and touch your nose. How are you doing that? What sense are you using to do that? You're not using your vision. Sort of. Scott said memory. It's a very specific kind of memory, I would say. Yeah, so it's something that, cognitive psychologists, we would call it proprioception, but it's basically muscle memory. So it's, how your muscles sense each other, how we sense the movement of our muscles, basically. Yeah, Alex.
I see what you're saying, where we definitely have a muscle memory thing, but in this particular case, could that also be simplified to a kind of, you're using a sense of touch because you can feel your whole body in a way as you do that, so you know where your body is to an extent by feeling it.
Yes and no. So there is a broader class of senses called somatosensation, which I have just like a sentence on, a slide in here. And somatosensation covers touch. It also covers proprioception. So, one of the difficulties is how do we decide where the boundary is between one sense and another? That's kind of difficult. Like we could, if we wanted to, say that color vision is a different sense than regular vision, if we wanted to, right? We could put a boundary there for whatever reason. And so it's difficult to even decide, like, how do we count? Yes?
Could you argue, I feel like you could argue that taste and smell are the same sense.
Some people could, yeah, they're very similar in the mechanic that they use. So they're often classified as the chemical senses, and they're put together kind of in the same family. But yeah, in general, there's kind of this difficulty of like, how do you decide a boundary? One of the ways is by looking at the physiology and looking at the different kinds of receptors. So the receptors that your olfactory or smell system uses are pretty different from your taste buds. So if we just look at those like physiologically, they're pretty different. And same with proprioception and touch. So I can kind of think of proprioception as like, it's this sensation that's very physical, but the receptors that do proprioception are very different from the ones that do touch. So that's why they tend to be, sort of classified in different categories. But yeah, there's all kinds of different ways that we could approach deciding where those boundaries are. But yeah, so another one, like if I asked you to stand on one foot right now, again, you might argue that's like touch, I can feel the floor, but it's more than that. It's a sense of balance, which comes from our vestibular system. So we have quite a few other senses. A lot of them are not very well understood. The other thing I'll mention too, I tend to geek out a lot on what's called comparative psychology, which is like looking at the differences between humans and other species. If we get into other species, then the list of senses is just like astronomical, right? You have some species that can detect magnetic fields. You can have some that use sonar or whatever, right? So there's like a lot of different senses if you start thinking broader than just humans as well. If it's something you're interested in, there's a really good book, kind of a side tangent, called An Immense World. I don't remember the author's name, but if that's something you're interested in, check it out. It's basically all about like different species and their crazy perceptual abilities.
When I was younger, I was a big shark nerd, and they
Oh,
were
yeah.
the ones with the electrical, that kind of electrical field sense.
Yeah.
That's why the hammerhead sharks have the hammerhead. That's like a like radar thing, kind of.
Yeah.
They're trying to find the rays underneath the sand.
Yeah, there's a ton of cool ones, and that book goes into like, I mean, there's just like a bunch of crazy ones that I've never heard of, and that just are kind of mind blowing to think about, like other species and how they sense the world and interact with things. It's crazy. I might reference a few of those, throughout here. Okay, so like I said, the whole basically job of perception is to take all this environmental energy and try to make sense of it and figure out where that energy is coming from, what does it mean, how can I interact with it, etc. The two main senses we'll talk about again are vision and hearing. And so we'll talk about kind of the waves that make up, those senses. So light and sound are both composed of essentially wave properties. The visible spectrum is a very small slice of this broader electromagnetic spectrum. So electromagnetic spectrum, again, just, a bunch of energy basically that's traveling in the form of waves. The whole electromagnetic spectrum includes things like gamma rays and X-rays, microwaves and radios. Obviously, we cannot see those, right? You can't look right now and see all these radio waves flying through the air, even though they're there. Instead, our visible spectrum is really just a tiny little sliver of that whole electromagnetic spectrum. And essentially, it always looks, I hate doing color things on a projector screen because the colors just never translate very well. But this is kind of showing our visible spectrum. It goes basically from purple to red. And each of those colors basically is just different frequencies of light. So frequency just refers to basically how quickly the wave is moving through the environment. Not quickly, that's a terrible way to talk about light. But basically the number of times that the wave repeats over, a course of time. We tend to measure frequency in hertz. So that just means that the wave is repeating itself that many times per second. So like a wave that's 1,000 hertz, that means that wave is repeating 1,000 times per second. Okay? And so like I said, each frequency we perceive as being a different color, essentially. We'll talk a little bit more about color vision in a little bit. So light has sound or has wave properties. Sound also has wave properties as well. So, as I'm speaking right now, there's just a bunch of sound waves that are traveling from my mouth out into the environment and eventually hitting your ear. And your ear has the job of trying to take all that and make sense of what it means and where it's coming from, etc. In general, humans can hear between 20 hertz and 20,000 hertz. That's if you have normal, intact, healthy hearing. We tend to lose the higher frequencies the older we get, especially if you expose yourself to a lot of loud sounds. If you go to rock concerts or you listen to your headphones at the highest volume really frequently, you will start to lose some of those higher pitch frequencies. My son, who is 14, often will hear just random sounds that I don't hear. We'll use the microwave or something, and he'll be like, "What is that buzzing sound?" I'm like, "What are you talking about? I don't hear anything." And it's because my ears are older than his, so I can't hear those higher pitches that he can still hear with his much younger ears. Again, other species have much broader ranges. So if you think about a dog, there's dog whistles that dogs can hear that humans cannot because it's way outside of our hearing range. It's way above that 20,000 hertz. So I've been talking about, hertz and pitch. Basically, they, have almost a one-to-one relationship. So we tend to, code the frequency of a sound wave as being a different pitch. So higher frequencies are going to have a higher pitch. Lower frequencies are going to have a lower pitch. So frequency, again, is just how often the wave repeats. The amplitude is how tall the wave is. And amplitude basically gives us volume. So taller waves are going to be louder, shorter waves are going to be quieter in general. So again, main thing to take from the last two slides is just this idea that light and sound both are basically just waves traveling through space that are carrying energy, and our sensory systems have to start trying to make sense of all of that. So let's talk a little bit about how they make sense of all of that, starting with vision. So vision obviously begins in the eye, but it only begins there. It does not end there. So we tend to think of vision as something that our eye is doing, but it's mostly something that our brain is doing. So the eye, the main job of the eye really is just to take the light and focus it onto the retina, which is at the back of the eye. So the retina is the sheet of neurons at the very back of the eyeball. So the front of the eye is basically just a focusing tool, essentially. So you have the cornea. The cornea is the outermost part of the eye, and it is a rigid structure that starts to focus the light. So the cornea cannot change shape or anything. It's just like this rigid structure that's kind of starting that job of focusing. So the light goes through the cornea, then it goes through the pupil, which is just a hole in the eye that lets the light in. And then it will go through the lens, which is positioned behind the pupil. The lens is also focusing the light, but the lens is flexible and can change shape. So whenever you're adjusting your focus, like if you look at something really close to you and then you switch to looking at something far away, it's the lens changing shape that allows you to kind of change where you're focusing your like visual attention, essentially. So cornea and lens both focus the light, but the lens is flexible. And then you also have the iris, which wraps around the pupil and basically just controls how large the pupil is, which is controlling how much light gets into the eye. So if it's really bright, that can start to damage the retina if too much light is getting into the eye. So the iris might constrict to try to limit the amount of light that's coming in. If it's really dark, it'll do the opposite. It'll dilate so that you can get more light into the eye to see better. All right, but again, all that fancy stuff is just doing one job. It's trying to get the light focused back here on the retina. So then let's take a look at what the retina does with that light. So this is like a cross section of the retina. Up here would be like the very back of the retina, and this would be the very front. So light is coming in this direction. And the retina is basically just this sheet of very specialized neurons, and it's highly organized. So it's sort of constructed of these 5 layers of very different neurons that all have a slightly different job in this whole process of basically taking information from the light, converting it to an electrical signal that the brain can make sense of, and then sending that information to the brain. So everything that's pictured in here are neurons. And I mean, these are drawings, they're not perfect, but they're a pretty good representation of what these neurons actually look like. So just from here, you can already start to see all that variation in neurons I was talking about earlier. So at the very back of the retina are a class of neurons called photoreceptors. So those are these here. And they're really strange looking. They don't look anything like the picture of the neuron that I showed you earlier. And there's different kinds of photoreceptors. Depending on the kind, they can look different. I think I have a slide on this in just a second, but the 2 kinds are called rods and cones, and that's because of their actual shape. So here you can see like the rods, they have this kind of rod-like shape. The cones have more of like a cone shape, so they're named basically for their shape. So the photoreceptors, this is a little counterintuitive, a little bit complicated, but the light is coming in this way, but the photoreceptors are actually the first cells that start to make sense of that light. So the light is traveling as what's called photons, which are just like little packets of energy, basically. When those photons hit the photoreceptor, it causes the photoreceptor to basically change its shape. It's kind of almost like a spring, basically. Like when the photon hits it, it's like a spring that kind of activates. And that causes that photoreceptor then to send an electrical signal, which eventually will make its way up to the ganglion cells. And then the ganglion cells send that information to the brain. Okay. There's lots of cells in between. They're highly specialized. They're essentially doing like mathematical computations basically on the light to try to start interpreting what that light means and what we should do with that information. Again, next Thursday, we'll probably have at least 1 or 2 visual illusions that will kind of highlight how the retina is starting to process that information. Okay, it's a lot of information pretty quickly. I see a few perplexed faces. Any specific questions about anything I've covered so far? Okay, so far we've got all these lenses at the front of the eye focusing stuff on the retina. The retina takes that information, starts to make sense of it, and send it to the brain. Like I said, in the retina, there are 2 different kinds of photoreceptors. Really, there's basically 4 different kinds, but it's kind of just like, how do we break it down? So there are rods and cones, but then there are 3 different kinds of cones. And the difference between those different kinds of photoreceptors is basically the way that they respond to different wavelengths of light. So because we have 3 different cones, they basically respond sort of preferentially to different wavelengths. So for example, there is what's called a short wave cone, which responds mostly to sort of blues and violets. So if you're seeing a violet or blue color, then those cones are like really excited and really active. There's a medium wavelength cone, which mostly responds to green. And then there's a long wavelength cone, which mostly responds to red. So when your brain is kind of trying to figure out like what colors do I see right now, it looks out in the environment and then it compares like, okay, this type of cone is really, really active, but you know, my long wavelength one is not very active at all. So I must be seeing, you know, red or whatever. So it's making comparisons between those 3. Yeah.
You have color blindness. Which one is the one that's missing usually?
Oh, that's a great question. So most people who are colorblind, they have what's called red-green color blindness, so they cannot see the difference between red and green. And I can never remember which one it is, but it's one of these 2. Yeah, they basically lose that ability to compare those 2, so then red and green look the same to them. Yes?
And it notes that there's 3 kinds of cones, but what about in the cases of 4 cones?
That's a great question too, and something I was thinking of bringing it up. So there is, it's called tetrachromacy whenever someone has 4 cones. It's a fairly rare sort of condition. It doesn't feel like the right word. It's a rare property that some people can have. It's been found mostly in women in like a very specific place in Europe. I don't remember where. But basically it's these people who have 4 cones instead of 3. And essentially what that does is it gives them the ability to see more colors than a normal person could. So if you like look at this spectrum, so, you know, at least to me, because I have 3 cones, I have normal quote unquote color vision. I see like red, orange, yellow, green, you know, cyan, blue, whatever. Like I see, you know, different sort of categories of colors within this. If I had tetrachromacy, then I would be able to see lots more variation within that same spectrum. So that's what having more cones typically does. Again, if we're thinking of other species, tetrachromacy is very common in birds, especially like predatory birds, like hawks and things like that. But instead of having cones that get, well, they probably have more variation in here, but they also have cones that are sensitive to like ultraviolet light. So, you know, having more cones can either broaden this spectrum, where you can see like infrared and ultraviolet, or it can make it so that within that spectrum, you can kind of distinguish more things. Good question. There's also, just because I'm already on the tangent, there's a species called a mantis shrimp. Any of you ever heard of those? They're these really crazy, colorful little like sea creatures. They're not a shrimp, they're not a praying mantis, but they just kind of look like both, so they call them that. They actually have 12 different cones. So like, you know, we try to imagine what does their world look like. They definitely can see ultraviolet and infrared, but then they also probably have a lot more variation within the spectrum. It's hard to tell because they're very difficult to do actual studies with. They're difficult to like train to do the kinds of tasks you would want to do to study because they just don't respond very well to like food and things like that. But yeah, dogs have basically red-green color blindness. So a lot of people hear that dogs are colorblind and they think like they see black and white or shades of gray. They actually can see blues and yellows pretty well. They just can't see reds and greens. So if you have a dog, you ever want to buy them a toy or something, try to opt for blues and yellows because they can see that a lot better than reds and greens. Any other questions right now about color stuff? Yeah.
I know that there's a color red that's within red that's actually not visible wavelength, but we've given it a name.
Oh, I kind of vaguely know what you're talking about, but I don't remember any details about it. Yeah. I don't remember. There's a lot of weird colors that are like, they don't have a one-to-one wavelength in the normal like electromagnetic spectrum because they're constructed in a different way. That's a whole nother tangent, but yeah. Anything else? I could literally talk about this stuff all day, so. Okay, so in the retina, we have rods, we have cones, just so you know, so rods are more important for seeing like contrast. And they're very important for like really low light conditions. So if you wake up in the middle of the night, you know, and you go to use the restroom or whatever, and your eyes like slowly adjust to the darkness and you get to a point where you can actually like see in the dark a little bit, that's your rods basically adapting to take in more light. So they're much better at like seeing contrast. Okay, so retina has all these different kinds of photoreceptors that take the light, start to make sense of it, send it to the ganglion cells, which eventually send it to the brain. So from the retina, information travels first to a structure called the thalamus. It's not labeled here, but it's basically right here, the structure here. The thalamus is one I usually talk about a lot when I teach a whole semester on sensation and perception. It's basically kind of like the little post office in the brain. It sort of takes in almost all of the sensory information, will make a stop in the thalamus. The only exception to that is smell. Every other sense makes a stop in the thalamus, and then the thalamus kind of figures out, like, okay, this is visual information, it needs to go to the visual cortex. This is auditory information, it needs to go to the auditory cortex. So it's kind of like a little post office, like sorting the information, sending it to where it needs to go. So from the retina, it first goes to the thalamus, and then it eventually goes back to the occipital lobe, to the primary visual cortex. One thing you might notice, it's kind of hard to see in this particular image, but the information also crisscrosses, which is very common in the brain in general. A lot of our sensory information and also motor output is crisscrossed so that like the left side of the brain controls the right side of the body and vice versa. And with vision, it's basically set up to where the left half of your brain is processing information from your right visual field. So everything you see right now that's on your right side, it's your left brain that's like processing that and making sense of that information. There are also parts of the brain, though, importantly, that get information from both. That's really important for like depth perception, to get information from both eyes and sort of combine that together, but that's not really shown here. Yes?
So, I just had a thought about the thalamus.
Yeah.
First time I've ever heard of it.
Uh-huh.
Did all the senses that kind of go into it and then get reorganized maybe evolve from the same sense, and then that's why they all share that area of the brain?
That's an interesting question. I've never heard it phrased that way before, but it seems I would have to kind of think about it too, because I think one of the first senses to evolve would have been one of the chemical ones, probably smell, which does not go to the thalamus. But maybe possibly after that, I could see where, yeah, maybe there was some sort of like the thalamus evolved as a structure to start dealing with all this different sensory information. I don't know. It's possible. I don't have a solid answer, but it's possible. It's a good theory that you should test.
It's a hypothesis, not a theory.
Yes. I'll agree with that. Okay. Okay, so from retina to thalamus, then back to the primary visual cortex. Then again, this isn't pictured here, but from the primary visual cortex, the information sort of splits into two like streams. So you have occipital lobe back here, primary visual cortex. Some of the information goes up to the parietal lobe, some of it goes down to the temporal lobe. The temporal lobe stream is basically just trying to figure out what you're looking at. So it's trying to identify what the object is. Like, this is a MacBook, this is a table, this is a thermos, whatever. The top one that goes to the parietal lobe is doing more like spatial information. So it's trying to figure out where things are located in space relative to yourself and relative to each other. So it's kind of doing that in parallel at the same time. Okay. That's all I'm going to say about vision. But again, it's something I could talk about for like ever. So if you have questions that you don't want to ask in here, feel free to come to my office hours after class. We can talk about it more.